Hi everyone, welcome to our presentation for the ICML. I'm Chen Yang. Our paper is titled with ATraDiff, Accelerating Online Reinforcement Learning with Imaginary Trajectories. So, a long-standing problem in reinforcement learning is how to improve the sample efficiency in online reinforcement learning, because it's always very costly to collect the data from interacting with the environment. And to tackle this issue, many researchers study different approaches, like developing sample efficiency algorithms. One possible way is data augmentation for reinforcement learning. Traditional data augmentation in reinforcement learning usually disturb the state of the transition to generate new data. While the generative model has developed a lot recently, we can use modern generative models to help data generation. So the key problem we started in this paper is, can we harness modern generative models trained on offline data and synthesize useful data that facilitate online reinforcement learning? So why we choose diffusion models as our base model in this work is that diffusion models have shown impressive capabilities in data synthesis across both vision and language applications, while in reinforcement learning, previous previous works in reinforcement learning focused on generation of transitions instead of trajectories. While we consider that the generation of trajectories can offer much more information compared with generation of transitions. So in this paper, our main contribution includes the several points. So we first propose ATraDiff, which is a novel diffusion-based approach that can generate full synthetic trajectories. And also, ATraDiff can integrate with a wide range of reinforcement learning methods. And we'll also introduce a simple yet effective coerced to precise strategy that ensures generation with flexible lengths. And we devise an online adaptation mechanism. So the main framework of our paper is that an iterative can be used uh, part of the data generator, which takes states from the real replay buffer, will collect data from the environment and generate new trajectories and put the generated trajectories with the synthesized replay buffer, and the agent can get those transitions for the online reinforcement learning. So our method contains several components. So first, we have a adaptive trajectory diffuser, where our diffuser suppose generation of both state level and image level trajectories. While in this paper, we found that the image level generation achieves higher performance compared with state level generation. So to have a union generation, we introduce an end-to-end state decoder and encoder, which can convert the trajectories from the state level representation and the image level representation. So here, our iterative originally generated state image level trajectories, and we can convert this trajectory into state level trajectories where can be directly learned from the agent. And we also have a coerced to precise strategy, which is used to cut the trajectories with arbitrary flexible lengths. In this part, we first have a length estimator, where can estimate the required lengths, and then from the estimated lengths, we select a generator to generate the trajectory. And then after the generation, a simple prune algorithm is used to cut the trajectory to a precise length. For the deployment, iterative can be applied to accelerate any online reinforcement learning algorithm with a replay buffer. So here we introduced a modified replay buffer to replace the original replay buffer. So the data collected from the environment will be added to the real replay buffer. Then our iterative take state from the real replay buffer and synthesize more trajectories to store in the synthesized replay buffer, and the agent can both fetch trajectories or transitions from the real replay buffer or the synthesized replay buffer to support the online reinforcement learning. And ICRADiff also contains an online adaptation mechanism where ICRADiff will update to the online real transitions. We have an indicator used to measure the importance of samples for the online adaptation. We are also combined with a pickup strategy to choose samples from the real buffer. Um, our experiments show that AcroDiff consistently improve the performance of online reinforcement learning methods across different environments. The main experiment of this paper shows that AcroDiff can further boost the performance of offline to online reinforcement learning baselines across different environments, especially in complicated tasks. Also, ITeraDiff can improve the performance of offline reinforcement learning methods. Uh, we also started some ablation studies in the experiment part. Here we show some important ablation studies. Well, the left one shows that the image generation can outperform the state generation, and the right one shows that the online adaptation strategy can significantly improve the performance. Thank you for listening. This is our project page.